As Conor said, my name is Marty Henning. I'm the VP of Solutions Engineering at Creative Technology. Part of my job is to lead the IP transition initiative. As Conor mentioned, we've been deploying 2110 for live events for about the last 3 years now, and have had the good fortune to work with all the manufacturers represented here today, from Panasonic to Matrox and Megapixel. And thanks to those guys, this has really been possible thanks to their support and engineering. Before we get started, I just want to take a quick minute to recognize a couple of individuals that have been instrumental in my journey over the last 3 years in learning about the networks that are required to support 2110. Ryan, Gerard Phillips, Robert Welch, John Mayhott, and Wes Simpson are all literal giants in this field. They're very active across SMPTE. You'll probably see them if you've attended NAB. They give talks there, Video Services Forum, etc. So if you are not familiar with their work and you're interested in what it takes to put together or you want to go deeper on what it takes to put together a network for 2110, I highly recommend you seek out some of their work. All right, in this session, we'll explore some practical strategies for designing 2110 networks, from simple setups to complex events workflows. We'll look at some common topologies, layer 2 and layer 3 designs, and we will cover managing multicast with IGMP and PIM. As the network scale, we'll look at how tools for automation and monitoring can simplify the deployment and management, along with the role of software-defined networking. Few design considerations as you start to look at your network needs. First thing is obviously identifying what you're trying to do and building your network to suit. One of the largest decisions is deciding on your management strategy, if that's in-band or out-of-band. Out-of-band obviously requires additional hardware, but it gives you some additional flexibility and reliability that you might not get in-band. Truth be told, you'll probably end up with a hybrid strategy, as a lot of the devices don't have enough interfaces to do out-of-band. Avoiding a non-blocking architecture is critical in the design, and we'll look at that in some of the design examples throughout the presentation. Room for expansion. If you build your network to suit exactly what you need today and you're fully maxed out on capacity, I think as you heard in the Panasonic demo, somebody's going to come along and ask you for something more shortly, and you'll be out of resources. And then finally, keep it simple. There are a lot of technologies, whether those are standards or vendor-specific tools, that sound really great and fancy, but you need to decide which ones are important and required for your network. And again, keep it simple so that it's easy to deploy and maintain. All right, first up in the network topology is the monolithic or flat collapsed, but it's a single switch. And much like the Panasonic demonstration, shares a lot of similarities with a baseband router. It's inherently non-blocking, and then every device is directly connected to that single switch. This is a really great place to start because it keeps the complexity low and lets you get some hands-on experience in the lab and focus on working with your endpoints rather than having to worry so much about the network and the network configuration. That said, redundancy is critical in live production environments, and it's actually one of the key benefits of an IP-based infrastructure. So as Conor said, 2022-7 is the seamless protection switching that makes sure that any packet loss or link failures on one side of the network don't ultimately affect the signal getting to the destination. As you can see, the topology is essentially the same as monolithic. It's just the red switch and the blue switch. Typically they're air gapped except for that little green line, which is to allow PTP traffic to pass between the two, so you make sure that you're staying unified in your clocking. But once you move out of the lab and into real world production, again, having the redundancy is key to a reliable network. Along the way, you'll undoubtedly run into some devices that don't have 2022-7 compatibility. They only have a single network interface for media, or maybe a single interface, period. And you can implement a hybrid, or what's often called a purple strategy, where you use either an additional switch or you manage the 2 switches that you have to allow that single home device to get access to traffic from both the red and blue networks. That works for both senders and receivers, but does take a little bit of tuning to make sure that you're not leaking flows from the red side into the blue side. The dual star is the logical evolution of the dual core network and is implemented for a couple of reasons. The first one would be topology. If you've got a significant difference or distance, between the nodes in your system, maybe it doesn't make sense to bring those all back over dedicated fibers back to the core. So being able to aggregate those sources in a leaf switch and then using a smaller count of fibers to get back to the core can be a much more efficient strategy. And then along with that, oftentimes in the core switch, you're going to have a bunch of 100 gig interfaces, and if your endpoints are 10 or even 1 gig interfaces, such as audio devices or simple 1-channel 3G devices, it's a fairly inefficient use of those 100 gig ports to be connecting 1 and 10 gig devices directly. So by using the leaf switch that might have a mix of 10 or 25 ports along with a few hundreds for uplink can let you make a lot more efficient use of the switch ports. You do need to be aware in this configuration and pay attention to your bandwidth needs to avoid oversubscription on the uplinks from the leaf switches to the core. Of course, if you've got a high bandwidth device, maybe that's a server that's doing some 4K outputs or some other gateway or say an LED processor that has an extremely large pixel space, it might make more sense to take that directly to the core rather than running it through your leaf switch just to preserve some of that uplink bandwidth. And then finally, your sort of ultimate network design is the spine leaf, which is an enterprise architecture that you're going to see in a data center or more specifically in maybe a broadcast facility. It's extremely scalable, it's extremely resilient, it has multiple links between all the switches, and you can see in the diagram that they're no longer red and blue specifically at the core, as they all have links that allow the traffic to pass between them, which means that not only can you survive an interface failure, but you can survive multiple switch failures and still maintain your redundancy across the rest of the network. Of course, this gets fairly complicated very quickly, and really to manage this type of network, you require typically a SDN solution or software-defined networking. This is a network control layer that sits on top of your broadcast control layer and actually manages the physical connections between switches and plays a part in actually routing the content across that network. Michael's got an excellent presentation on PTP, so I'm not going to go into great detail here. I do want to include a couple of quick tips in the topology section about PTP. It is the most important source in your network, and it's responsible for keeping everything in sync. So two critical factors are redundancy, and you can see in this diagram there are multiple grandmasters there at the top, but making sure that your network has access to the same time all the way across. So in addition to each grandmaster being directly connected to each core switch, there's also a path between the core switches so that if you're to lose a link, you don't suddenly end up with the blue switch on an island trying to be its own grandmaster that's separate and offset from the red side. And I also wanted to point out that in all of my diagrams, we're showing GPS providing the ultimate time reference for the system. In live events, we don't often have the benefit of clear sky access. So while this is nice, it's not strictly imperative in a single system deployment as long as you have a high quality grandmaster with an accurate oscillator that can be trusted to maintain consistent time or consistent frequency and time. The one thing that I'll caveat there is that you need to be particularly mindful in any sort of failover scenario, because without a specific time and phase reference, which you get from satellite-based time it's possible that if there's a recovery after a failure, you could experience a time skip, which of course could be disruptive to the content on the network. Last thing about this before I move on is the boundary clock is really recommended to help manage the traffic across the network and take the load off of your grandmasters. And again, managing the priority settings to ensure that the failover behavior is exactly what you expect it to be. All right, into the traffic management. Different types of traffic that you'll see on the network. Of course, there's broadcast traffic, that's one to all, unicast, one to one, and then multicast, one to many. And I expect by now everybody in this room knows 2110 relies on multicast traffic, so the majority of this section is going to focus on managing that multicast. Each of the media flows that we've been discussing is generally mapped to a unique multicast group. The multicast address range spans from 224.000 to 239, 255, 255, 255, and this is split up into sub-ranges. Some of them have some fairly unique purposes that you need to be aware of, and I've called those out on the slide. If you want to take a look at the entire range and the specified uses, there's an RFC for that, 5771, if you want to go deeper. As is listed here, the first range is a local subnetwork. It's not routable, and it's used for control protocols on the network like IGMP, PIM, OSPF, and MDNS. So this is definitely an area that you want to avoid in your multicast addressing scheme. And then the next segment there is for internetwork control. This is routable, but is used by services like PTP and NTP. So again, this is an area that you want to avoid. As I mentioned, everything between 224 and 232 is in the multicast range, and it is available. Most of it does have a specific purpose, which might not be in use in your network, but before you make the decision to use that range, you should at least be aware of what its intended function is to make sure it's not going to cause you any problems. The majority of the deployments that you'll see will be done in either the 232 section, which is specified for source-specific multicast, or the 239, which is designated for private use. So now that you've decided to use 239, you have to come up with a scheme to actually assign to all of your senders. The temptation is to come up with a human-readable format that lets you decode maybe the location, the device type, if it's on the red or blue network, maybe the flow type segregated by video, audio, and metadata, and then maybe a specific flow on the device. And in small networks, that's certainly a feasible approach. But once you, again, grow beyond a certain scale, it's not very efficient in terms of address allocation. And eventually, you could find that you're out of addresses to use, and you won't be able to maintain that scheme anymore. So best practice is to use a summarization approach, which will give you some information about what the flows are, but not quite at that level of detail. So an example of summarization might be to break up your flows by network, red or blue, and then further segment them into video, audio, and metadata, as you see on the left of the slide. And then what that lets you do is specify them in larger chunks. So all the red flows could be summarized by 239.000/10, which is then helpful when configuring the switches, say rendezvous point in PIM, or perhaps ACLs to limit leakage in the purple scenario that we looked at earlier. In layer 2 networks, IGMP is the protocol that's responsible for controlling the multicast traffic, essentially preventing multicast from becoming broadcast. The job of the querier is to inspect the join request and make sure that only the requested multicast groups are sent to a specific port or device. And then it's the job of the querier to sort of check in over time and make sure that the devices that are on those ports still actually want to receive the message, the multicast groups that are being sent there. Source-specific multicast is a feature that was introduced in IGMP v3, and what that does is it allows a receiver to specify which sender of a specific multicast group that it's interested in. So in IGMP v2, the receiver simply says, I want multicast group 239.121, and if there are multiple senders sending to that same group, both of them will be sent to that receiver. By specifying the source IP, you get a little bit more granularity and control over exactly what's being received at any time. It's important to note that while IGMP is backwards compatible, if you mix and match it on the network, it's often a case of the lowest common denominator, in which case you'll lose those benefits and everything will operate at the V2 standard, which will eliminate the single source multicast. All right, and then outside of some vendor-specific solutions, once you get out of a single switch into a multi-switch deployment, the IGMP query lives on a single switch. In order for it to do its job, all of the multicast traffic has to be flooded to the query, which can result in link saturation, especially if the receivers in your network are on the same network segment as the sender. There's no reason to send it to the query if there aren't any consumers there. And then in addition, in layer 2, the multicast group addresses are mapped to MAC addresses, and because of the way that was done, you end up with 32 multicast group IP addresses that all correspond to the same MAC address, meaning that if you are using one of those IP addresses as your multicast group, or more than one of those multicast IP addresses in your system, subscribing to one could result in you receiving them all in a layer 2 network. Fix, or the solve for that, outside of those vendor-specific solutions, is transitioning to a layer 3 solution or implementation, at least on the links between switches. That will eliminate the flooding to the query as the multicast is managed locally on each switch, which gives you some flexibility in scaling, as well as provide some isolation for any failures. So if somebody creates a loop on a switch and you end up with a spanning tree problem, or a broadcast flood, it's not going to crash your entire network. It'll be limited to the switch, where the error happened. And similarly, if you end up with a misconfigured device on the network, having that layer 3 implementation gives you some additional resiliency in the network. Layer 3 uses slightly different protocols from layer 2. PIM, or protocol independent multicast, specifically in sparse mode, takes over the job of IGMP on the layer 3 segments and only forwards the streams to interested receivers. And then OSPF, or Open Shortest Path First, automates the routing table updates. So as your devices are connected together, you don't have to create manual routes for those sources to be able to find the flows that they need. That's handled automatically for you. When you start thinking about adding layer 3 links into your network, you've got some flexibility. Again, as I mentioned, the links between switches are a fairly critical place for layer 3 implementation, but it's still acceptable in some networks to have all of the access ports on a switch in a single layer 2 VLAN. But then you can, of course, expand the layer 3 domain down to individual switch ports. So every single switch port is its own layer 3 network, really has 2 hosts, the connected device and the port itself, in which case you've isolated the failure domain, again, for any misconfiguration or loopback links or anything like that. So again, identifying your network needs and your tolerance for risk and simplicity, and trying to make decisions that are appropriate in your network. As you get out of the layer 2 domain and into the layer 3 domain, you have to have some additional consideration for your DHCP scheme. In a fixed broadcast facility, creating a scheme for static IPs for either layer 2 or layer 3 is really straightforward because the devices tend not to move around. However, in a live event environment, static IPs can become challenging. as the devices need to move around the network for each deployment. There are a couple of strategies that you can implement within DHCP to manage this. Of course, option one is to manage it locally on each switch, and again, perhaps down to the port level, where every port is its own /30 with a DHCP server. DHCP option 82 could allow you to host a central DHCP server and then use the option 82 details to understand where that device was connected and assign the addresses accordingly. In live events, again, we're trying to make the system as flexible as possible, understanding that we're not going to have a network engineer necessarily on every deployment. So we're trying to keep things as plug and play as possible. To that end, even a mid-sized network can be relatively complicated to configure. And anyone that's ever managed a switch in CLI knows that can be time-consuming and a confusing process. The benefits of automation, I think, are pretty clear. It offers consistency. Once you decide on what the configuration is and you've programmed it into the automation tool, you reduce the possibility for human errors. Efficiency. I can only type so fast, and I know I'm not very accurate either. So if I can again program it once and let the machine do it after that, it's going to be a lot more efficient in the long run. And then of course scalability. Once you get past more than just a few switches, trying to manage those configures in a live event environment is quite daunting. The common use cases, which I think I already covered, the initial switch provisioning. Beyond that, compliance checks. If you're in a live event rental situation and you are sending equipment out in the field, maybe some changes or updates happen while it's in the field. When it comes back, it's got to be turned around to go out again. Being able to quickly compare the existing configuration to what the default or stock is. Automation can streamline that process for you, as well as taking care of software updates and then backing up and restoring configurations. The one option for automation is a tool called Ansible. This isn't a sales pitch. This is an open source IT automation tool that's pretty common in the industry. It's agentless, which means it doesn't need anything to be installed. It can use SSH or API to interact with your endpoints. It uses playbooks, which are essentially divided up into plays that are individual bits of your configuration that are then tied together with variables that let you create complex configurations with reusable parts. And then, of course, like I mentioned, it's open source and has multi-vendor support, so you can use it with the vendors, all the major network vendors. So now you've got your network built, you've got your multicast managed, and you've got your automation set up for deployment. Now you just cross your fingers and hope that it runs smoothly. Or you start thinking about network monitoring and visualization. Step one is data collection. SNMP it's been around for quite some time. It's widely supported, and it does a good job at what it does as far as letting you collect data from your individual switches and bring them into a central repository. Telemetry is push-based. It's going to be higher frequency than SNMP and is available from some vendors. Because it's can be vendor specific, might need a little bit more work for integration, but if it's available, it's a great option to have to get at those critical metrics. Once your data is collected, you want to do something with it because all that raw data can be pretty daunting. There are several tools available for visualizing the data that's been collected. By organizing it into dashboards, you can give an operator a great sense of the health and the status of the network, essentially at a glance. And then you can also use what's called exclusion monitoring to bring alerts and potential problems up to the top so that you can act on them in a timely fashion. The dashboard that's here is not 2110 specific, but when you get to the megapixel presentation, you'll get to see some Zabbix dashboards that were used on the network at the Eurovision Song Contest, which are a great example of some of the features there. Software-defined networking. I know Conor talked a little bit about software-defined, and I think it's a bit of a buzzword that gets thrown around. And after the talk yesterday, I had several people comment on this, so I just wanted to point it out here. Software-defined networking really complements everything that we've talked about so far. And where it's really key is when you get into large and complex networks, especially with multiple uplinks between switches. The centralized control nature gives a lot of flexibility for management and offers improvements over the network protocols like PIM and IGMP, and the hashing algorithms that are used to balance traffic across multiple uplinks. The SDN controller is bandwidth aware, where the standard network protocols are not, and allows deterministic routing. So you can program some logic into the decisions about how you want to get traffic across your network. And then, of course, it can be responsive to link failures. It's aware of the state. And by implementing an SDN solution, you can effectively scale your network well beyond what's reasonable to manage with the inbuilt network protocols alone. And then finally, the key takeaways. Your network design matters. Choosing the right topology and making sure that you're set up for your future expansion and your future needs. Multicast management, whether that's a simple layer 2 network or spine and leaf that's layer 3 at every single port. You need to have a strategy there going in. And then, of course, IP addressing schemes and assignment, not just for the multicast groups, but for the sources as well. Monitoring and automation. In a fixed facility, you can get away without the automation, but again, in a live event environment, it becomes critical. And then, of course, the monitoring really is what allows you to be proactive versus reactive. A specific example of that, we had an optic failure on a show recently, and because of the 2022-7 redundancy, the failure was invisible to everybody that was watching the screens or the sources. However, because it came up in the alerts box on our monitoring dashboard, we're able to dispatch a technician, go correct the problem, and get that network back on the air before it ever affected the production. And then, of course, software-defined networking. There are various solutions, vendor-specific and some they're more agnostic. But this is really the Cadillac level of network design and management. Again, working with your broadcast controller to manage the network in a very specific way that helps normalize some of the abstraction that you get after you stack up so many different layers of networks and protocols and control. The SDN solution can really help keep it under control.